On this episode of MRI Physics Explained, we continue our journey in understanding K-space by taking a deep dive into the world of Fourier transforms. This is first and foremost a mathematics lecture, so don't be scared by all the MRI physics talk if you're here for other reasons. But understanding Fourier transforms also happens to be the key to understanding how MRI machines work, along with all that you love in the modern world, so buckle up and have some fun as we learn about Fourier Things on this episode of MRI Physics Explained. Hello everyone, and welcome back to this advanced MRI lecture series titled How It Really Works, where we're going to escape the MRI physics education simulation we've all been trapped in and learn the truth about image building and K-space. Dr. T.E. and Tim Kerrigan, MD here. We left the last lecture on quite a cliffhanger. We revealed the roadmap to understanding K-space, and while there is no best starting point in this endless cycle of intrigue and misery, an understanding of the Fourier transform is absolutely critical, and so we shall begin here. It's the year 2000. You're young and full of energy and want to change the world, but those ambitions will have to wait because something more important just happened. The hottest new album of the year just dropped, and you can't wait to get your hands on it. Do you know what the top-selling album was in the year 2000? That's right, our good friend Eminem's Marshall Mathers LP. Hello Eminem if you're watching this video. I hear he's a closet MRI physics fan. So you're dying to get your hands on this CD, but you have a problem. You're flat broke. You have no money. And CDs were like $20 back then. Crazy. But you're in luck because your best friend just bought the CD, and he goes, I'll send it to you for free over the internet. So you fire up your cutting-edge compact PC with the 56K modem. Log on to AOL.
You got mail.
And begin the download. And you wait, and wait, and wait. The anticipation is killing you, so you decide to do the math and figure out just how long this is going to take. The CD is 700 megabytes, and you have a 56K modem. So we have 700 megabytes divided by our 56K modem, which can transmit data at 56,000 bits per second, and we need to convert bits into megabytes. We run this calculation and come up with a time of 100,000 seconds, which equals 1,667 minutes, which equals 28 hours, and the grim reality now sets in. It's going to take you over one whole day to download this album, and that's if your dad doesn't kick you off to log on to his AOL account to watch cat videos. But you're obviously not the run-of-the-mill kid. You're going so far as to calculate the time it'll take to complete this download, and your ears cannot wait a day longer to be blessed by the genius of Eminem. So you search, deep down in your soul, for a clever way to speed this process up, and you come to a revolutionary realization. You know that the normal hearing range of humans is 20 to 20,000 Hz, and ask yourself, do we actually need any frequencies outside this range to enjoy our music? Why would we need frequencies that we can't even hear? Is there a way to eliminate these inaudible frequencies? We'll come back to this, but we have yet another problem to solve. It turns out we also have a side job making our Hollywood celebrities look better than they actually are. The job doesn't pay well, we can't even afford a $20 CD, but hey, at least it's something, and Brad Pitt reaches out in distress. They took his photo at a red carpet event and are about to publish it, but he has too many wrinkles. He asks, no, he pleads with you, can you do anything to make me look younger? Well, is there? And this sets the stage for our discussion on the Fourier transform. But first, if you enjoy these videos, consider liking and commenting, following us on social media, hit the join button to see ways you can support us further, and click that subscribe button below. So as logic would have it, if there's a Fourier transform, then there must be a Fourier. This is the guy who's going to make magnetic resonance imaging possible, as well as bring us into the digital age, and his name is Jean-Baptiste Joseph Fourier, a French mathematician and physicist from the 1700s, and I apologize to all of our French audience out there for how badly I'm butchering his name. But Monsieur Fourier came up with a monumental realization that any periodic function can be represented by summing harmonically related sinusoids together, what we call the Fourier series. Allow me to illustrate. We're going to use some pretty outlandish examples to show just how powerful this is. Let's start with this square wave. It's a repeating or periodic function, but with extremely sharp transitions, and you ask yourself, how can a sinusoidal wave ever recreate something like this square wave? Let's start with an initial sinusoidal wave cleverly centered on the square wave so they have the same period. Let's now add another wave to the first. And another. And one more. You can see with just 4 iterations, we have something that's starting to look pretty close to this original square wave, and if we keep going, we're going to get closer and closer to the actual wave. So what is going on here mathematically that makes this happen? This formula is an example of a Fourier series using the sine-cosine form. Now, if you're not big on math, don't worry, this is not a math test. Forget all the intricacies at first, we're going to keep our focus on the big picture of what this is saying. Let's take this formula and apply it to this ugly looking periodic function on the left, s of x. We know this function, right? At any point along the x-axis, we know the corresponding value of s. And the overall period of this function, the time it takes to repeat, which is 2 pi in this case. Going to our equation on the right, it says that this function is going to be equal to this initial coefficient, a sub 0, plus the sum of these coefficients weighted by cosine and sine waves, a sub n and b sub n, for however many n cycles we choose. So the question is, what are these coefficients that we'll need to do this calculation? The first coefficient, a sub 0, equals 1 over the period times the integral of our original function s of x. We only need to know s of x, our original function on the left, and its period to calculate this coefficient a sub 0. Next, we need to know this coefficient a sub n. What is the formula for a sub n? While it looks more complex, in the end it just consists of our original function s of x, its period, and some math. What about b sub n? The same story. We only need to know s of x and its period. So while this looks horribly complex, the truth is in order to solve this messy looking formula, all we really need to know is the original function and period. And the more iterations we run this equation, the closer we approximate the true original function. Let's take a look at this visually. The blue lines on this new figure represent our function on the left, and one by one we'll add these sinusoidal waves together using the above formula and see what happens. As you can see, the more we add, the closer this approximates the original function. In this example, our n equals 5 iterations of the above formula. Here's an even more radical shape. We can't possibly create this out of sinusoidal waves, or can we? Now it took a few more iterations than last time, but you can see after 10, it's already eerily close to the original function. Let's keep going and see what happens. You'll notice that as we add more and more waves, we get closer and closer to the original function. But also notice there's a law of diminishing returns here. At some point, adding more changes the shape less and less, with these areas of extremely sharp transition the most difficult to resolve, what we call Gibbs phenomenon for all you MRI artifact lovers out there. And while it does get closer to the original function the longer we run this, it's going to come at the cost of increased computing time, so in practical applications, there will be a point we're going to have to say this is good enough. The cost of more iterations will provide little benefit. So this series of sinusoidal waves added together after a number of iterations is what we call the Fourier Series. And then we have something called the Fourier Transform. Let's say we have this periodic function, and we find the first 6 sinusoidal waves of our Fourier series. Here we are seeing what those individual waves look like before they're added together, and notice there's a sort of method to the madness here. The first wave matches the period and overall frequency of the original function, and then each successive iteration creates waves that increase in frequency. That's what this term is doing. As n increases, this term, which corresponds to our frequency, gets larger and larger. Looking at this graphic from this side, you can see our individual waves start with the highest amplitude and lowest frequency and progressively goes to smaller amplitudes and higher frequencies as this process goes on. So this original wave can be reconstructed from individual waves of progressively decreasing amplitude and increasing frequency. We call this process the Fourier Transform, taking this original function acquired over time, finding the simple sinusoidal waves making up this function using our Fourier series formula for however many iterations we choose to perform. Notice that in this process, we're going from this time domain, our original function plotted over time, into a purely frequency domain, a listing of the frequencies and amplitudes from the simple waves that, when added together, recreate our original function. Okay, all you MRI physics fans, where have we used this tool called a Fourier transform before? Why yes, in our signal localization lectures. This is where we took our raw MRI signal and broke it into the simple sinusoidal frequencies making up that complex raw signal. One last thing to point out here. This process is bidirectional. We can do what is called a forward Fourier transform, where we go from this original function, our raw signal in our MRI physics example, into the simple waves that make up that function. We can also do the reverse. If for some reason we have a collection of simple sine waves, we can perform an inverse Fourier transform where we add these together, recreating our original function. This is a lossless process. We can go forward and back, however many times we like without losing information. So with this newfound knowledge, let's go back to our dear friend who's in the pits of despair because of how long it will take him to download the new Eminem record. Over one whole day before the real Slim Shady can please stand up. But our friend is smart. He happened to watch this video on Fourier transforms and says, aha. What if my friend sending me the CD performs a forward Fourier transform on the raw music? We can then see the individual frequencies making up each song, and since we know humans can't hear anything below 20 Hz or above 20,000 kHz, let's delete these frequencies we can't hear. This is simply extra data making our download unnecessarily long. After deleting these, we can simply perform an inverse Fourier transform on the remaining frequencies, reconstructing the songs on the album minus these unnecessary frequencies, and in doing so change this 700 megabyte CD into a 70 megabyte MP3. That's right, folks. You can thank Fourier transforms for technologies such as MP3 that made peer-to-peer internet music sharing possible, which is a whole nother story in itself. Now that we have a 70 megabyte MP3, we've decreased our download time from 28 hours to approximately 2 hours, and our friend has never stopped singing the real Slim Shady ever since. Now that we've solved this problem, let's see how Brad is doing. To recap, Brad is having a bad day. He's getting his picture taken on the red carpet and is concerned that he has too many wrinkles and wants to look young again. He also knows you've seen this lecture on Fourier transforms and begs you, please help, I'll do anything. What do you think? Can we help him out? Why yes we can. It's subtle, but we've introduced just the right amount of blur into the picture that those harsh lines from being married to Angelina Jolie all those years have been smoothed over and are less apparent. How did we do this? Well, it might not be as apparent in this case since we're working with an image and not an audio recording like in the previous example, but we in fact did the same thing. used a Fourier transform to see the frequencies making up this picture, deleted the ones leading to those harsh lines, and then converted it back into the picture. It is this process that you must understand in order to figure out how MRI machines create images. So for those of you here for the MRI physics portion of the lecture, we're going to now focus our attention on how these Fourier transforms fit into our theory of image building. Let's review the steps we've learned so far as to how our MRI machine generates signal and builds a picture. All of these have been covered in depth in the previous lectures, links to which I'll pin into the comment section below. Step 1. We apply a slice select gradient and tune our RF pulse to the Larmor frequency corresponding to our slice of the body we want to image. Step 2. With the system energized and producing signal, we'll blip on and off our phase encoding gradient, inducing a phase shift between rows or columns of voxels in our image depending on which axis we choose. Step 3. We apply our frequency encoding gradient across the other axis while recording the signal generated by our echo. This brings us to the step with the Fourier transform. Through the phase encoding and frequency encoding gradients, we've embedded information into the raw signal that we can then use to locate the signal coming from each voxel within our slice. The Fourier transform is used to identify the frequencies that make up this raw signal. In this case, the columns within our slice will each have their own frequency. As you can see here, the CSF and soft tissue voxels share the same frequency, as do the fat and bone voxels, albeit a different, higher one, because our gradient goes from low to high across the slice. But this isn't enough to localize the signal. We need to pick a time point with which to compare these two waves and record their current at this time point. We then have to repeat this process for however many rows or columns of voxels we have along the phase encoding gradient direction. In this case, we have a 2x2 voxel slice, so let's go through these steps one more time. Step 1, our slice select gradient. Step 2, our blip with the phase encoding gradient, albeit using a different one this time. Step 3, applying our frequency encoding gradient during the echo while recording our signal. Step 4, applying the Fourier transform to get our frequencies out of the complex raw signal. Step 5, measuring the current again at the same time point as before. And finally, using our systems of equations to solve for each voxel along the phase encoding direction, all of which is discussed in great detail in the dedicated phase encoding lecture. With this information, we can appropriately calculate the magnitude of the T2 decay curve coming from each voxel in the slice at our time point TE and place it in the correct spatial location, which allows us to build our contrasted picture when a color scheme is applied. Again, this is a super quick version of what's covered in the original first 4 lectures, but hopefully this refreshed your memory. So going back to our Fourier transform discussion, in this instance, our raw MRI data is this, the signal acquired over time. And we applied a forward Fourier transform to get the frequencies that make up this raw signal, shown here. Are we good so far? But as we covered in our previous lecture, we know there's a problem with the standard theory taught by most MRI physics courses. Under this method, we have problems with k-space. There is no need for it. We know it's not feasible to accurately generate hundreds of these systems of equations we just covered needed to localize the signal, and it doesn't explain how we can run a sequence such as HASTE, where we acquire only half the data needed to generate a picture and are able to generate a picture at all. So it's the moment you've all been waiting for. The problem lies right here in front of you, and with the most subtle of changes, the path to how this all works falls into place. This whole time, we've been relying on the assumption that after we capture our raw MRI data, we apply a forward Fourier transform to break it into our underlying frequencies from which we build our picture. But the truth is, our raw MRI data is actually this, frequency data. And to build our picture, we in fact perform an inverse Fourier transform. Now, I'll admit this is a confusing and quite outrageous claim, and in order to convince you this is how it really works, I'm going to prove it to you mathematically as well as visually, and that's what the remainder of the lectures in this series will be aiming to do. But first, we need to start thinking about this process in higher dimensions. One of the reasons this is hard to understand visually is that what we're saying is this complex function in fact represents our two-dimensional picture. We'll go into depth on this in a later lecture, but I want to begin prepping your minds to think about this process in higher dimensions. If this two-dimensional picture is our complex function, what will be the two-dimensional version of these simple waves representing our raw MRI data? They're going to be planes, sinusoidal waves with depth. And with that little taste of what's to come to ponder over, we conclude our lecture on the Fourier transform. On the next episode of MRI Physics Explained, we made the most outrageous claim, and now we're going to back it up. We're going to prove to you mathematically that our raw data is frequency, and our image is the product of an inverse Fourier transform by deriving the most important equation of magnetic resonance imaging. Thank you for your support as always. I hope you're enjoying this new lecture series and can't wait to see you next time. This is Dr. T.E. for Tim Kerrigan, MD, signing out.